This is a video for advanced child pupils who may wish to get a recap on the equations of motion work from higher physics. The equations of motion can only be used when there is motion in one dimension with a constant acceleration. So things like air resistance are ignored because if there was air resistance, the acceleration wouldn't be constant because there would be a force acting upon the motion. Let's look at an example of a car accelerating from rest at 4 meters per second squared. And we're asked to work out its velocity after 10 seconds, how long it takes to travel a certain displacement, and how far it has gone after a certain time. So, like any question, start with listing out the data that you have. So it starts at rest, so the initial velocity u is 0. The acceleration is 4, and we've got the time being 10, and we want v. So we can see that's the first equation of motion, v equals u plus at, to give us 40 meters per second after 10 seconds. How long does it take to travel 72 meters? So now we have a displacement, 72. We don't have a time. We have our acceleration, we have u. We pick our equation of motion, this time s equals ut plus half at squared. And because we've got 0 times t, the first term cancels, and we end up with 6 seconds. How far might it have travelled after a certain time? Then list out our quantities. S is what we're after, t is the time, a is 4, u is 0. We can use s equals ut plus half at squared and solve. Okay, so strategy, list the data. Sometimes you might want to make a sketch to ensure that any vector quantities are being listed in the correct direction. So in that case, the previous example, the car was just going in a straight line, so the direction was in the direction the car was moving. Sometimes it's different. Okay, let's have a look at vertical motion. So if we're looking at things falling down, then often we set downwards as being negative and upwards as being positive. If it's free fall on Earth, the acceleration will be the acceleration due to gravity, 9.8 meters per second squared. But it could have a different value if it's not in free fall or if it's in a different place. So let's look at the example of a stone dropped from second floor window 15 meters above. Must be flats because that's quite high up. How long does it take for the stone to reach the ground, and what velocity is it when it hits? So we've got initial velocity of 0 because it's dropped, and we're making the acceleration and the displacement negative as it's going downwards. What's the time taken to reach the ground? We can substitute in all those values into s equals ut plus half at squared, and because we've got a negative 15 and a negative 9.8, the negatives cancel out to give us a time of 1.7 seconds. Sometimes if there's initial velocity upwards, if it's thrown upwards, we need to take that into account, so that would be positive, and then downwards motion would be negative, usually. It's only a convention. You can make it the other way around, but you're more likely to confuse yourself. Let's just have a look at some graphs to compare. So we've got an acceleration graph, its equivalent velocity time graph, and its equivalent displacement time graph. So no acceleration means constant velocity, horizontal graph, horizontal line on this graph in the middle, and the displacement graph has a constant gradient. We'll also recall that the displacement is equal to the area underneath the velocity time graph. So constant acceleration, constant horizontal value for the acceleration, then that comes from the velocity time graph, which has a constant gradient, and then the displacement time graph will be a curve because the object is speeding up, so it will be traveling more distance in a certain amount of time as it gets faster. Negative acceleration, then that means the velocity is going from a greater one to a lesser one, and eventually it stops, so the displacement graph curves off and flattens to a particular value when it's not moving. We could have graphs like this one, and we could get information from that, from the acceleration, or we can get the displacement. So we could get the value for the initial acceleration from the gradient of the graph, or the value for the final acceleration for the gradient of the graph, which in this case is minus 15 divided by 6, because we're looking at the second part of the graph. We're looking at this part here. Or we could do v minus u over t to get the same response. Okay, let's have a look at a different example. Find the change in velocity in the first 5 seconds and between 0 and 30 seconds. The change in velocity is the area under an acceleration time graph. So in this case, 3 times 5 gives this area here, 15 meters per second. It's the change in velocity in the first 5 seconds. It's then not accelerating, so it continues at 15 meters per second. It then slows down for 10 seconds, and we got this bit here. This should come down to 0.3 meters per second in the opposite direction. And that's going for 10 seconds, so 10 times minus 0.3 gives us minus 3. So the overall change in speed, change in velocity, is 15 minus 3, which is 12.